So today we're going to be doing DT8, which is dive planning. We've skipped a couple of lectures ahead because a lot of them are very practical based, and obviously we can't really do that at the moment. So we'll come back to those at some point once we can kind of get in person a little bit. What we're going to cover today. Oh, hold on. Tell you what, let me fix this instead to that. You guys still see the PowerPoint, yeah?
Yeah, okay.
Yep. Cool. Why, Leo? Just no, go away. Right, so what we're going to be covering is basically planning diving as a dive leader. So the aims of this lecture is to teach you a little bit about planning and the role that the dive manager has in planning diving, why we want to do the dives, who's going to do the dives, where we're going to do the dives, and when we're going to do the dives, and what else is required. It's not very descriptive, but we'll go through it and see what we find. So, role of the dive manager. You guys are now relatively experienced, some of you, unlike Leo, who's an ocean diver. So you guys are going to be leading people on dives now. You're going to be role models, and people are going to be looking up to you. Obviously, a couple of you are instructors, so that goes even more so for you. As a dive leader, you're going to be qualified to dive lead and plan dives at known dive sites. Okay, so certain roles that you could be appointed to when you're a dive leader, for example, is the dive manager, which is what this lecture is all about. So you're appointed by the diving officer, which is me, and basically your responsibilities range from organising the day of diving to delegating to assistant dive managers, to having not ultimate but very high level authority on stopping diving for a single person or the whole group. The only person who can overrule you with that is the diving officer. And I mean, for example, you could stop someone if they're hungover, or in the case of the club, drunk, for those who are aware of that little incident last year. But yeah, you're kind of responsible for making sure that the diving happening is to the letter and not going off the rails a little bit. So like I mentioned, you can make your job a little bit easier by delegating these tasks. So those who have done sports diver already, which is all of you hopefully, will have gone through the assistant dive manager stage. I know Joel's finally got that ticked off now, so I can say that all of you have done that. So collecting those details from divers is a very labor intensive task, which means if you as a dive manager take it upon yourself to do all of that as well as trying to organise the diving, it can be a little bit messy. So it's better to delegate that. You can also liaise with other support roles, so such as kit officers or boat officers in terms of organising kit. Obviously, as James knows, there's a huge amount of organisation that goes into making sure equipment is ready for diving. Fills, maintenance, making sure everything's the right numbers, you've got spares, you've got equipment to repair any damage, that kind of stuff. So there's a huge amount of coordination that goes behind the scenes, and the dive manager is responsible for ensuring all of that is done correctly and on time. You'll also start taking on responsibility for rescue and surface support. The dive manager is the default rescue manager. So if there's a rescue situation, by default, the dive manager is the person who's in charge of that. Sometimes that's overruled if there's someone more senior, so perhaps the diving officer's there. But generally, as a dive manager, you're going to be in charge of rescue scenarios. Obviously, when it comes to that, it's good to have some basic information before all of that happens. So collecting information such as who is first aid trained, who's able to administer oxygen, that sort of thing, is really useful. So if it does happen, you know exactly who you can call on. We've already talked about equipment, but basically you make sure that all the equipment is ready for the dive. Although you don't have to personally go along and make sure the fills are done, make sure all the regulators have ports in, or even have hoses attached correctly, James? I know that was Mike, wasn't it, who had a hose unscrewed in the pool. But you don't have to personally do that. You just need to make sure that's been done properly by the kit officers. So one of the first things you'll consider as a dive manager planning dives is the objectives and the divers that will be doing those dives. So step one really is what type of dive do you want to do? Are you going to be just diving for the fun of it? Are you going to be doing some sort of training, or is it a combination of both? Obviously, there's unique considerations between each of those points. If you're just diving, it's a little bit less difficult to organise because there's a bit more freedom on who can go with who. But also, you've got to think about the environment. So if we're training, Stony Cove is a great environment because it's enclosed. You can't really get lost like you could in open water ocean. And there's the depths in that area are quite helpful to training. So we have a 6 meter platform, which is funnily enough where we do most of our skills, and then a 20 meter platform, which is also the next step in that skill, and then a 35 meter plateau, which is the next step in the skill. So it's the depths of the plateaus are very helpful for us. So that's something you'd want to consider if you were organizing a training trip. Whereas if you were just doing fun diving, that wouldn't really be as much of a concern. You also need to worry about how many divers. Now, if you're doing shore diving, like at Stony Cove, yes, there is a certain amount of consideration with what equipment you have and perhaps how many instructors you have available, but nowhere near as much consideration as boat diving. So those who went up to the Farne Islands know that even though there are very few of us on that boat, space was not exactly a premium. So making sure that there's space on the boat for diving is quite important, and so you will need to limit the number of divers. You also need to consider about the minimum diver grade. So again, for Farne Islands, most of those dives required a DSMB to be deployed, which means ocean divers can't really do those dives without being paired with a sports diver. So then we kind of come on to what kind of grade and experience level that we're going to be having and buddy pairings for that. So like I said, if you need to deploy a DSMB, that doesn't necessarily entirely rule out ocean divers. It just means they'll need to be paired with a sports diver or above who can deploy that DSMB. You also need to be thinking about training. So do you need to be pairing them with an instructor? Do they need to be with a full instructor, or could they have an assistant diving instructor? So there's a little bit of background documentation to look over there. Also just general diving and you know, what do people want to do? Are there any special interests in the group? So photography, or are there kind of nitrox or rebreathers? Because we all know those nitrox dives are right pain in our asses. Not looking at anyone in particular. But making sure that people are matched up with fairly similar equipment setups is very helpful, because there's no point putting a rebreather diver with someone on a 10-litre cylinder, because the whole point of the kit is they can go for longer, and you're restricting that by the buddy pairing. So trying to balance that a little bit. Something else they don't really mention on the slides, but also friendship groups. You know, if someone particularly wants to dive with another person, try and keep that in consideration, because it does make diving a lot more fun. I'm sure you guys know. So talking about dive sites, you guys will be qualified to lead diving and manage diving on known sites. So the point of this is, you know, the site characteristics. So whether it's a boat or shore dive, whether there's any sort of variations in depth, I'm sure you all know now what depth Stony is at. The general conditions that can happen underwater. If you didn't know Stony, you probably wouldn't expect the visibility to be that bad sometimes. And then kind of areas of interest and known to you as well, where you can go. And then the facilities as well. So surface parking, access to the actual dive site. I've done dives where we're going down little alleys or very narrow single track roads where both wing mirrors are being hit by bushes on either side, so access is pretty restricted. If you wanted to bring a larger van, like Kev's van, for example, might be a little bit wider, that could restrict you. So taking into consideration that sort of thing. You also need to think about cylinder filling. Now, typically we try and organise it so we don't have to pay for fills, but if you're going into a remote place and you can only take so many cylinders, you need to think about where you can get those cylinders filled. That's a really big consideration for us. And also any changing and toilet facilities you can find. Although most divers can live without these, it's nice to have and know where they are. And also refreshments. Do you need to bring food and water, or can you get away with buying it there? And then one of the biggest points really is accommodation. If you're organising a trip anywhere, you need to know what the accommodation is. That's very easily 50% of the organisation. So that's a really big point there. And ultimately, does everyone know how to get to the dive site? If it's in some far-flung area, does everyone actually know the directions to get there, or are you going to end up with some lost cars? So some other little points on site information and location. Source of information that you can get this sort of thing from. charts, which we'll look at in a couple of slides, tide tables, which again we'll look at in a few slides, and then weather information. There's a load of different sources for weather information that range from BBC Weather all the way to like BBC Radio 4 for the shipping forecasts, which we'll again come back to. But this is really important source of information for divers. As we know, weather can have a huge effect on how we do diving and whether we can even do it in the first place. And then if you're boat diving, you want to make sure that you have access to a GPS, an echo sounder, and any sort of transits. If you don't know what transits are, we'll be coming to those again at a later point in this slideshow. So a very quick recap on gas planning. This isn't a large section, so don't worry. But up until this point, you've all worked at a 25 litres per minute consumption rate. And that's assuming a calm diver. Now that is relatively conservative, but it's still sometimes quite valid for perhaps new trainees. In an emergency, for example, when someone's out of air, and particularly when we're diving deeper than 35 meters or we have an invisible ceiling from decompression, we need to start considering our emergency gas consumption a little bit more and whether that 25 litres per minute consumption is actually valid anymore. Truth is, it's not really. So in an emergency or you're stressed out underwater, your breathing rate rapidly accelerates. It's very often above 25 litres per minute. Sometimes you can get kind of 50 litres per minute, even 70 litres per minute, depending on how quickly someone's breathing. So this is going to be a real consideration for your gas planning, particularly when you're doing deeper dives, which are harder to get to the surface in an emergency. So let's say we have an out of gas situation with a buddy pair, and this dates this slide a little bit, an aqualung system, the scuba set. Your breathing rate for your casualty is probably going to be in the region of 50 litres per minute because they've just run out of air. They're going to be shitting themselves. Your rescuer could be on 25 litres per minute, or they could be equally terrified and also doing 50 litres per minute. For the sake of the example, let's assume combined they're now breathing 75 litres per minute off the rescuer's set. So what does that actually mean for us? So if, let's say we're at 35 meters, assume a kind of 10-minute per meter ascent, which is pretty standard, relatively quick, but not insane. That takes about 3 minutes to get to the surface. So a little bit more time for sharing, getting the holds ready, kind of figuring out what's going on, all that sort of thing. Extra minute, I'd say that's pretty quick. It's more likely going to be 2 or 3 minutes, to be honest. And then at that sort of depth, your absolute pressure is 4.5 bars. So combine that all together with your breathing rates. That means in the 4 minutes it takes us to get to the surface, off a single cylinder, we will breathe 1,350 litres. Now what that means is, if you have a 12-litre cylinder that's fully filled, that's just under half of the cylinder in 4 minutes. So when we realise that most of these emergencies happen kind of midway through or at the end of a dive, potentially you might not actually have enough air to do this, which is why we really need to be on top of this sort of planning, and why the rule of thirds, particularly for deeper diving where ascent times could be limited by decompression stops, we need to take that a bit more seriously than we have done in the past, maybe. So moving on to something that's probably totally new to a lot of you, the chart system. So I've got an example on the second slide, but we'll very quickly go through this. So who here has seen a chart before? Hands up, just very quickly, or knows what they are?
Me.
I'm sure Kev's seen the entire set of charts in the world. Is that only 2 of you? Okay. So some of this is going to be new to you guys. Some of it will probably be, preaching to the choir, but we'll see how we go. So your charts are basically maps of the seabed. Like you have OS maps of the surface, a chart is a nautical map of the seabed. Okay, you've got loads of useful features on them. We'll cover what those features can be in a little bit, but first it's important to know how we locate ourselves on that map. So the Earth, as you can see pictured, is split up using a grid reference system. So we use a grid. So we have horizontal lines of latitude, or we call them parallels of latitude in pink, and then we have our vertical meridians of longitude in the blue. Okay, so you see how on the flat chart at the bottom, that's a square grid, but on the planet, it's slightly warped. Now keep that in mind because we're going to come back to that and why that's important in a minute. So just as a quick example of what a chart looks like, this is a Farne Islands chart with a couple of hand-drawn arrows to show tide, but don't worry about those for now. You can see that we've got loads of different, let me get a loads pointer, loads of different numbers scattered all over the graph. Any idea what these are?
Depths.
Depths, bang on. So there are depths. You'll notice even way out here, our max depths are kind of 50 meters, really. So it doesn't go hugely deep in the grand scheme of things, but it can vary quite quickly. So here we have 11 meters and now it's 20 meters. Especially around the islands, you have these lines. Do you see the lines? This dictates the gradient of the depth. So they are isolines and they'll go along a gradient. So we'll come back to the features of this in a little bit, but I just wanted to show you what they kind of look like because there's not really any good examples on this slideshow. So you'll see on this particular chart, we've got these grid lines. So they're quite big, but at the top, it's been cut off. Top and bottom, you'll have numbers on them as well. So if I can skip to the next one. So let's have a quick look at the latitude and how we devise latitude. I'm sure those of you have done map reading before, and this is going to be very boring, but latitude is your horizontal lines. Let's say we have a plane in the middle of the planet at the equator, okay? That plane, the angle between the plane and the north and south pole is 90 degrees. Everyone follow that so far? Yeah. So let's say we now make a second plane a certain distance up and then measure the angle from the center point to the point that that plane contacts the surface, and that gives us 50 degrees, okay? And now let's draw that plane line all the way around on the surface. That line is denoted as a 50-degree line, or the 50 degree parallel of latitude. So you can see on this little diagram here, 50 degrees is up there. And then we do that the same for each degree as we go up. So equator is 0 degrees. And then as we go up, it'll increase to 30 degrees, 50 degrees, and so on, all the way up to 90 degrees at the North Pole. You'll notice underneath, though, we do exactly the same thing. It increases 30, 50, and so on, all the way to 90 degrees at the south. With the equator dividing it, north and south, that means with our coordinate system, we'll need to denote whether our latitude degree reading is a north reading or a south reading. We'll see that in a moment when it's written out as well. Looking at longitude, so let's say we look down from the planet. So we're looking from above the planet here. So North Pole's right in the middle, okay? And we split that up into sections, okay? And each section we assign a degree to, with 0 degrees on this side of the circle, and then go all the way around to 180 degrees, sorry. We do the same thing on the other side. So we combine the two, okay? And then we kind of project those lines through the planet all the way to the bottom, and that splits the planet up into segments like this. So everyone's had a chocolate orange, right? Please tell me everyone's had a chocolate orange. That's going to make me really sad if someone hasn't. But this is basically what chocolate orange looks like, yeah? So it's all in these segments, and each segment denotes a certain degree, okay? So these lines are then drawn on the surface of the planet as 30 degrees, 60 degrees, and so on, all the way round to 180 degrees. Now, again, you'll notice that each side of the 0 degree line, it increases. So this is split vertically between west and east. So we'll denote west and east. So again, when we're given a degree, we need to make sure we note it's either an east or a west reading. The 0 degree line is internationally recognised as running through the Greenwich Meridian, which is in London, funnily enough. So there's a line that literally runs through London, which is 0 degrees longitude. Okay, so let's combine those two together. And now we've split the planet up into grid sections based on degrees and north, south, west, and east. So it's really important you give the full reading. So we can't say, let's say we're, what's that, up here, something like that. Okay, So we're 50 degrees up here and 30 degrees that way. Now that could either be here, that could be here, that could be here, that could be here. There's 4 different locations that could be. So it's important that we denote that we're actually north and west. Okay, so that would be this position here. Does everyone follow why we're there and how that relates to this particular point? Everyone happy with that?
Yep.
Cool. If you're unhappy at any point, just put your hand up and I'll cover it again. So our positions are given in degrees, okay, because we split it up into degrees like a circle. And we can split those down further into minutes. So 1 degree can be split into 60 minutes, okay? Now BZAC teach a minute can be split further into 100th of a minute, so 0.01 minute. Sometimes you'll see seconds, which are a minute divided by 60. So there's 60 seconds in a minute, and then 60 minutes in a degree. So you'll see some slight difference, but when they're fully written out, they look like this, okay? So you have your degrees in this column with a degree symbol next to it. You have your minutes just here, and then your seconds or your hundredths in that final decimal, and then your north, west, east, south denotation. Okay. Now, this relates to our measure of speed because 1 minute on the chart relates to a single nautical mile. So a minute across the chart is about 6,000 feet, which is 1 nautical mile. And then in terms of precision, 1 degree will give you kind of so if you gave a bearing or a location rather in this format where you just give degrees, that would produce a search area of 100 kilometers, which is pretty big. If you gave them minutes, so degrees and minutes, that reduces it down to about 1.9 kilometers, which is still pretty big. But if you gave them the full 3-figure denotation, that will reduce it down to 30 meters squared. Okay, so as long as you give those 3 figures and the northwest's signs, that will give you quite an accurate reading as to where you're going. Now, if we were actually trying to find a wreck based on these coordinates, 30 meters is still a big place to search. So you're going to need an echo sounder to locate that. Okay. One final important point on this is you'll notice on this diagram, if we just go back a couple of slides to the square map as well, notice how on the globe, which is real life, these lines look bent. Yeah. But on the map, they're perfectly straight. So when we're converting a spherical chart to a flat chart that we can print on paper, there's going to be some sort of distortion, which we mentioned before, okay? And that distortion is important because when we go all the way back to the slide we were on, it's important because you'll need to use latitude scale to measure any sort of measurements you're doing, okay? The reason being is when you're looking at a chart, if we're going, this is going to get really old very quickly, isn't it? Go back to the final. We've got a latitude and a longitude, okay? Our latitude scale, so let's say that is 1 nautical mile. I'm assuming, I don't know the scale of this map. That latitude scale is going to be correct. So you could literally measure that distance and it'll be correct, and you can transfer that to the rest of the map. But if you use that longitude scale, that's going to be distorted ever so slightly, and that's not going to be accurate. So it's really important to use latitude. Wink, wink, definitely not asked in the exam. So moving on, finally, how do we actually transfer this into a real life situation? So we use something called GPS. I'm sure you've all heard of it and you all know exactly what it is. It's a load of satellites that help you navigate. So based on 3 satellites, we can fix the position and we can denote that through that coordinate system that we've just talked about. And that means we know the boat's position at all times when we have a GPS unit on the boat. But we could also get the GPS coordinates of a dive site, put that into the GPS unit, and then that GPS unit can actually calculate a course, very similar to Google Maps like you'd use in a car. it'll tell you a distance to the site, and then it will actually give you a quick little notification when you've gotten on top of the site. Now, like we said before, even a second denotation for the chart is going to be a 30-meter area. So you will need to bring an echo sounder to make sure you can pinpoint the site, unless you're diving a huge wreck or there's a shot line with a buoy on top of it. That makes it really easy. So how do we actually use these for planning? Chart 5011 identifies all the features on the chart. Consider it a key to your chart, so it'll tell you all the different symbols that you can get. So there's all sorts of stuff on it. You get coastline features, depth contour lines, seabed information, hazards, tidal flow information, etc., etc., etc. There's loads of information on it. I don't think it's available free, unfortunately. You'll have to buy it. Most of the time you can figure it out, but we'll have a quick look at some of the features just to give you an idea. So you can see we've got dry land is denoted as yellow, with prominent features marked on dry land. Why would we be interested in prominent features on land, particularly towers? Interestingly, there's 2 towers marked on there. Any ideas why that might be useful?
For doing transits.
Bang on, doing transits. General locationing. So we'll come on to transits in a moment. Areas that uncover with tide is green. Okay, so that if you leave a boat there at high tide, come back at low tide, you're not going to have a very floaty boat. And then if we have a slightly more zoomed in look, you'll see that the sea is mainly white, but shallow areas can be blue, just to kind of highlight that they're quite shallow. You'll also get these depth contour lines, which you mentioned before, and then your depth soundings, so your depth readings, okay? You also get a reading of the type of bed, so there's a key for these. They're not very intuitive, but you tend to get sandy, rocky, gravelly, that sort of thing. So it will kind of describe the seabed. So that's quite useful for divers because we don't want a silty bed. So if we pick a dive site that's gravelly, that might have slightly better visibility, for example. This is one of the most important things for us as divers, obstructions. So this little symbol, the number with a dotty circle around it and an underscore on it, that means there's some kind of obstruction at 1 meter. So that's the depth. And for boats, that means avoid, because you don't want to hit those. For us, it means go to it, because it might be a good dive site. So that's quite an important little symbol for us. Talking about transits, do we all know what transit is? Am I preaching to the choir, or do you not really know? Hands up for those who are not really sure what transit is. A couple, cool. So let's say we're doing a nice little boat dive off the coast. We can still see the coast. We're not out into the middle of the ocean or anything. And we can see on the coast, get the laser pointer up, we've got some buildings down here and a big tower and some trees up there. And we know that our dive site is right where this boat is. So we can denote that position or remember where that position is by lining up certain features on the land. So some prominent features we've got here, we've got some sticky up chimney there and a big spire there. So that's quite a good one to line up. So lining up 2 features at a certain distance away from each other will end up with that dotted line, and then that fixes your position. Does that fix my position entirely? Is that going to be enough to actually be at the right place?
Surely not, because you can be too far forward or backwards.
Absolutely.
Oh, really cool.
Absolutely. So the boat could be here, the boat could be further away. Yeah. So you've got a line, it gives you an idea. So you could combine that with saying it's a mile offshore and use the GPS for that. But absolutely. So what we can do, let's have another scenario. You'll notice that we've got pretty coloured in highlights, so you know exactly where the lines are going to be. But you see how we've got a wreck underneath that we want to go to. We've got 2 transits now. So we've got this one. The peak of that rock is in line with this building when we're at the right place. But again, we could be anywhere along this line. But then if we combine that with a second transit, the peak of this, it looks like a buoy or something. With that spire, we've got this second transit. And now when they cross over, we have a single point. And that denotes that exact point where we want to be. Does that make sense to everyone?
Yeah.
Yeah. Cool. So again, this is ocean diver really, so I'm hoping you all know this. our depths and our tides, we know that spring tides, oh, it bloody says it where I can't even ask you. So spring tides are the greatest tidal range, okay? So that's when your moon and the sun is in line with each other and their gravitational forces combine. So at low water, the water's really low, and then at high water, the high water's really high. In contrast, your neap tides, they have the least tidal range. So that's when the moon is at a 90-degree angle to the sun. They're out of phase. So your high water is, or rather your low water is higher and your high water is lower. So the tidal range is smaller. We see that on the diagrams. Okay. So we can actually predict the tides with tide tables. So entirely predictable. This is what a timetable looks like. And we calculate these for standard ports. So you'll find these for normal ports that are fairly commonly visited. So there'll be one for sea houses, which is up in Farne Islands. There'll be one for Portsmouth, Plymouth, and so on. So they're specific locations because the times and the heights change for different places. They're usually in universal time. Okay, so bearing in mind, if we're on the time-saving schedule, we'll need to add an hour as well. So just do bear that in mind because it can catch people out sometimes. And it also gives you your high water and your low water times. Okay, so you see this column, it says time, and then we have these times. They're in 24-hour format with no separation in the middle. So, but you should all really be able to read those. So that gives you the time for high water and low water. And then obviously it's going to give you your depth. Does it say it on the PowerPoint? I don't know. Back to it. It also gives you your depth in meters. Okay, so fairly obviously this is high tide in the middle and then low tide on either side. I think that's fairly obvious. With spring and neap tides, you'll notice that we have higher high water. So you'll notice, where's a good example? So high water here is 4.7 meters. Okay. High water a couple of days later is 6 meters. It's the same place. It's just spring tides coming on. So, like they say, we notice that the tidal range changes massively. Okay, so tell me what the tidal range is for the 22nd, roughly.
5.6 meters.
Yeah, pretty much. And then the anyone else go on?
2.4.
There you go. So about 2 meters. So you can see it can change quite a lot. Okay, so this should all be common sense for you guys at this point. The real question is, actually go back, why does the low tide never go below 0 or even get to 0? That's the question. Any ideas?
Wouldn't be it would just be land then. It wouldn't be sea, and it would be a bit land, wouldn't it? Because you would be able to see it.
So what are these depths? I know it sounds like a stupid question, but what do these depths actually correlate to in the real world?
Like how much water is above the bottom?
Okay, so let's say this is for the middle of the ocean and we have 0.5 meters. Do you know anywhere in the ocean apart from a harbour that gets to 0.5 meters? Not really. So the trick with these tables is to realise that these are not depths as you'd normally consider them. They're Chartan depths, which is what we'll cover now. So it's a little bit of a trick question because I haven't taught you this before, but Chartan depths on your charts, so these numbers that we mentioned earlier, they're depth marked at the lowest possible level that the water could be. Okay, that does not include the water above the chart datum, so your tides. So when we were looking at those chart tables, so this is a little excerpt from the chart table, we had 1.5 and 5.5. At this particular location, we had 24 meters of depth, but you add the tide table depths on top of that. So at low water, it's actually 25.5 meters. And then at high water, we have 29.5. Does that make sense? I'm assuming everyone's nodding. So it's a little bit of a trick question, to be honest, but you need to remember to add that on top of your Chartan depth. That isn't the absolute depth to that. So if everyone's happy with that, I'll move on to tidal flow. So we all know how tides work. We all know that slack water exists at either end of those tides. Everyone's nodding. How do we predict these tides and how do we work around them? So we have something called tidal diamonds. So you'll see on charts these, funnily enough, diamonds with letters in them. And they're placed strategically around the map at certain points. And at the top of the chart, you'll find a table. That's what they look like. They're very hard to read unless you zoom in. So that's what a tidal table looks like, and they relate to the tidal diamond. So you can see here we have a diamond with an A in it, and here we have a diamond with an A in it. So we know that that correlates to this particular location. Okay. So this tells you the hours before and after high water. Okay. So you see high water is marked with HW, and then we have hours before high water and hours after high water. It also tells you the direction of the flow. So we have DIR, direction, not do it right, and a set of numbers. What are these numbers?
Bearings.
Bearings, compass bearings. So this will tell you the direction of the water flow, okay? Bearing in mind, geography doesn't change, tides don't really change that much. So this is always going to be accurate unless you have a major change in the geography. So perhaps you've got a wreck that's sunk near that tidal diamond and it's changing the tidal flow. But these are generally the same every single year, year on year. It'll also tell you your speed. So you've got your rate, which is speed. And what does KN stand for? Anyone?
Knots.
Correct, Mundo, Mr. Sailing himself. So that's knots. And then SP is spring tides, NP is neap tides. So it gives you a speed in knots. Okay. Cool. One of the last little elements that we're going to look at is the compass rose. So you've got an outer compass and an inner compass. So we've got an outer compass here and an inner compass. Now, we all know that the North and South Pole are at the absolute center of the planet and never change, yeah? Not quite. They move every year, which is really unhelpful. So what we've done is we've had this outer compass, which denotes true north, which means, or basically it means like it's the point where you go from south to north pole at the center of the planet, and that never changes. That's always constant. And we draw our charts based on that. We then have an inner compass for magnetic north. So when the magnetic field shifts on our planet, it will move ever so slightly. And that'll tell us the relationship between magnetic north and true north. So bearing in mind that true north is used on charts, we might have to adjust our compass bearings to account for the magnetic deviation, or declination is what it's called. Now, on this particular one, it's saying 10 degrees declination, which is massive. In reality, it's about 2 degrees in the UK. So I don't know about you guys, but I can't get a bearing accurate to 2 degrees. So in reality, this isn't going to bother us that much. It aligns along true north, blah, 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 blah. Basically, this is all what I've just said. You can use this for tidal flow information. So if you want to check the direction of your tidal flows, that's all given in your true north again. So you've got to convert it for magnetic north if you're using a compass to try and orient that in the real world. Inner compass aligns to magnetic north, blah, 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 and so on. Very quick one on weather planning. We all know the effects of wind. Wind generates waves and sea swell. Do we all know what we mean by swell, by the way? Anyone not know? I assume that's a yes. So obviously the waves depend on the wind direction and the strength. It also depends on the fetch, which is the distance that the wind has to affect onto the top of the surface of the water. So if you've got a fetch which is hundreds of miles, so going from Cornwall to the Mexican peninsula across the entirety of the ocean, that's a huge amount of fetch. And so a very small amount of wind can make very large waves. In contrast, if you have a fetch like the English Channel, it's very short distance in the grand scheme of things, and you probably won't get that much waves for the same amount of wind. So that's another factor for it, which I don't actually mention. This can affect underwater visibility. Your swell is going to move water subsurface, and so that can stir up silt on the bottom. So that's definitely something that we need to consider. And also, waves aren't particularly fun to be on a boat with, to be honest. If they're particularly strong, it's not very enjoyable. So that's something we should really plan on as a dive manager. You also need to think about rain and fog. Massively reduces the surface visibility, particularly around oceans. This can set in incredibly quickly. We're talking a couple of minutes, not hours, minutes. And if your navigation is based on transits, you're kind of screwed if you can't see the transits. Okay, so just keep that in mind. If you're using transits, keep an eye on the weather. Make sure you're not going to have a fog cloud come over you. Temperature is also quite important to think about, especially on the boat. If you're hot, you'll get hypothermic because we have dry suits on and we don't take them off because we're stubborn. But also if you get cold, if it's very blowy and galy, you get hypothermic, so you get really cold. So it's definitely something to keep in mind about, and think about what we can do to negate that, whether people need to wear waterproofs or windproofs to try and keep warm, or whether they need to bring sun cream and cold drinks. So just it's something to plan around, really. In terms of weather forecasts, I'm sure all of you have heard of force, like gale force winds and force 5 winds and that sort of thing. That relates to the Beaufort wind scale. So that goes from 1 to 12. So force 1 to force 12, force 1 being very calm winds, force 12 being total hurricane, end of the world winds. Anything over force 4 can make diving pretty uncomfortable, both on the boat and in the water because of surge. And really, it's only safe to dive in protected sites in that particular type of weather. But to be honest, even then, it's not particularly enjoyable. You can get this sort of information from your shipping and inshore forecasts, which are broadcast on BBC Radio 4, local radio stations, TV. You can get on websites, I'm sure. You can even get it off the Coast Guard website, I think. So there's lots of different sources for these. They're typically only for about 24 hours. And they describe it in a very strange way, which you'll cover in Advanced Diver, but all you need to know is force winds at that point. So they'll say it's a force 3 wind or something like that. That's pretty much it. So we went over the idea of planning with the role of the dive manager, the kind of site information that you'll have and you'll want. Very quick look at charts, just introduce you to those, and tide tables that come along with those, and the sort of weather information and where you'd get it as well. We also had a very quick look at boat diving and the site location and the equipment you need for that, and any kind of special techniques that you'd need for entry and that sort of thing. So are there any questions? Once again, dead silence. I don't know if that's a good sign or a bad sign. Cool. In that case, if no one's got any questions, thank you for coming. That's DT8. I'll stop the recording now.